All right, here's the video for 9-5 tests about means. So just a reminder, when deciding between z and t, with proportions, we always use z. But for means, we have to know the population standard deviation, and our sample size has to be greater than or equal to 30 in order to use z. Otherwise, we should be using t. So the same rule follows with hypothesis testing. So here's an example. Several cities have begun to monitor the paramedic response times. In one such city, the mean response time to all accidents involving life-threatening injuries was mu equals 6.7 minutes with a standard deviation of sigma equals 2 minutes. The city manager shares this information with emergency personnel, encourages them to do better next year. At the end of the following year, the city manager selects an SRS of 400 calls involving life-threatening injuries and examines the response times. For this sample, the mean response time was x bar equals 6.48 minutes. Do this data provide good evidence that response times have decreased since last year? All right, so this is a one sample mean hypothesis test. So we need to figure out if we are using z or t. Well, we do have our population standard deviation, as well as a sample size greater than or equal to 30. So this example, we are going to be using z. So in step one, we're going to identify our symbols. So first of all, our sample size says an SRS of 400 calls, which means that n is 400. Mu, it gives it to us here. It says mu is 6.7 minutes. So that's going to be 6.7 minutes. X bar, our sample mean is 6.48 minutes. And then lastly, sigma, we're also given that is 2 minutes. All right, in terms of our null and alternative hypothesis, well, our null we know that it's a one sample mean problem, so it's going to be mu is equal to 6.7 minutes. And our alternative hypothesis, we want to know if mean response times have decreased since last year, so less than 6.7 minutes. Okay, where mu stands for the mean response time for life-threatening injuries. Or for, I should say, for calls involving life-threatening injuries. All right. In terms of conditions for tests about means, just like always, independence and random condition are the same. Big N is greater than or equal to 10N, and the randomness should be stated. However, with means, when sigma is known and our sample size is greater than or equal to 30, to meet the normal condition, our sample size just has to be greater than or equal to 30. All right, so let's check our conditions. The independent condition, big N, which is going to be all calls involving life-threatening injuries. Is greater than or equal to 10 times 400. So this is calls within a year. It's definitely reasonable to assume that there's over 4,000 calls involving life-threatening injuries. So reasonable to assume. The normal condition, 400 is our sample size. That's definitely greater than or equal to 30, so that's good, which means it's approximately normal. And for our random condition, I believe it does say SRS, yes, so SRS is stated. All right, so in terms of calculations, again, when sigma is known and our sample size is greater than or equal to 30, the general form for the test statistic is this, but more specifically for means, when we're using z, it's x bar minus mu over sigma over the square root of n, where mu sub 0 is the value of mu specified in the null hypothesis. In terms of finding the p-value, it's the same deal. All right, when we're looking for greater than, we subtract from 1. When we're looking for less than, we just look it up the value in our table. And when we're looking for not equal to, we're looking to the values of both tails. So we look on the negative side and multiply by 2. So let's calculate our test statistic now. So x bar was 6.48. mu was 6.7 over sigma over the square root of n. So putting that into our calculator, we get negative 2.2. So remember, we are using z in this case. And then our alternative hypothesis had a less than symbol because we're looking for probability that's decreased. So we're trying to find the probability that z is less than negative 2.2, which means that we should just be able to look up that value in our table, and that will be our p-value. So negative 2.2 is going to be 0.0139. So there's our p-value. All right, so now our conclusions in context. So I'm going to say since our p-value was 0.0139, it's less than alpha of 0.05, we reject our null hypothesis. We have statistically significant evidence to conclude that the mean response times to calls involving life-threatening injuries is less than 6.7 minutes. So again, you state your p-value, decide whether to reject or fail to reject. Since we're rejecting our null hypothesis, we're concluding the alternative in words. So instead of writing that, I just said it verbally. All right, so let's do another example. Okay, so the other example is going to involve some data. So I'm going to go ahead and put that data into GeoGebra. All right, so here is the data in GeoGebra. So now let's do one variable analysis. So first of all, we're going to check for any outliers. So there's no outliers since there's no numbers on the outside. So now we're going to have our statistics here. All right, so our sample size in this case, so this is about, these are levels of dissolved oxygen in a stream. So in terms of our sample size, there's 15. Since there were no outliers, we didn't eliminate anything, so n is equal to 15. The mean that we're looking at, we're comparing the dissolved oxygen levels in our stream to 5 milligrams per liters. So that's going to be mu. X bar we're going to get from GeoGebra, our sample mean. It's going to be 4.7713. And our sample standard deviation is going to be 0.9396. Okay. So now let's state our hypotheses. So there's a one sample mean problem. So mu is equal to 5 milligrams per liter. And then mu, it says a dissolved oxygen level below 5, so less than 5 milligrams per liter, where mu is the level of dissolved oxygen in the stream, or the mean level of dissolved oxygen in the stream. All right, so in terms of conditions, the independent and the random condition are the same as before. So big N is greater than or equal to 10N, and the randomness should be stated. However, for the normal condition, we're going to check the normal quantile plot since we know that our sample size is less than 30. All right, so in terms of the conditions, so our sample in this case are randomly chosen locations along the stream. So big N is just going to be all locations, which we know is basically infinite because you could take a sample anywhere along a stream. That's greater than or equal to 10 times 15. That's definitely reasonable to assume. Okay, for the normal condition, we're going to need to go to GeoGebra and check the normal quantile plot. So normal quantile plot is here, and again, we're looking for it to be roughly linear, which we can see that this is roughly linear. So normal quantile plot is roughly linear. And then lastly, the random condition, it says randomly chosen, so that's stated. Okay, in terms of calculations, it's going to be relatively the same. However, we know that we're using t in this case since our sample size is less than 30 and we don't know sigma. And then the only thing that changes in our equation is instead of using sigma, we have to use S since we're not given sigma in this problem. In terms of finding the p-value, since we're using a totally different table, finding the p-value is a little different. So here are the steps when using the t-table to find p-values. So first of all, we're going to look at how many degrees of freedom. And remember, degrees of freedom is always n minus 1. Remember, if the value is not there, we need to round down. So for instance, if you say that there's 35 degrees of freedom, 35 is not on here, so we would use 30 in that case. Okay, then what we're going to do is we're going to look in that row to see which t star values fall around our value of t. So we can ignore the sign since our distribution is symmetric, right? Generally, negative t values are here, positive t values are here, but these areas are symmetric, and our t-table actually only gives us the upper tail probability. So it's kind of the opposite of our z-table, but we can basically just ignore the sign, look at the absolute value of t. So once we find those values, we look at the upper tail probability for those t star values. So let me just look at an example. So here's our null and alternative hypothesis. We have our sample size and we have our test statistic. So in terms of degrees of freedom, we're looking at 14. So that's the row that we're going to look at. And our test statistic is t equals negative 0.95. So since we're looking for less than, we know that we're looking for, if we were to sketch a picture, this is negative 0.95. We're looking for this. Our t-table only gives us greater than, so that's why we can just look at positive 0.95, and that'll give us the probability that we want. All right, so 14 degrees of freedom means we're looking at this row right here. Okay, and what we're doing is we're trying to find where would our t star fit in this distribution. Well, our t is 0.95 or negative 0.95, but we're ignoring the sign, so it's going to be between these two values. So these are the test statistics that we have, and we have their corresponding p-values. So the corresponding p-values, or the area of the area to the right, is between 0.15 and 0.20. So we don't know what it is, but our p-value is somewhere between there. We know it's less than 0.20 and greater than 0.15. All right, so let's go back to our example. So now let's calculate our test statistic. So x bar is 4.77 minus the mean that we're using, which is 5, divided by s, 0.9396, over the square root of 15. All right, so our test statistic is negative 0.95. Negative 0.95, which was actually our example. So negative 0.95. Okay, so again, kind of walking through what we just did. We're trying to find the probability that t is less than negative 0.95. So I'm looking at our picture. Again, this is negative 0.95. We're looking for this area, which means that we can find this area, and it's going to be the same thing. So just like we did, it's 14 degrees of freedom. And our test statistic is somewhere between these, which means our p-value is going to be between 0.15 and 0.20. All right, so now our interpretation in context. So since we don't have a value for the p-value, we're just going to state our range. So I'm going to say since our p-value is somewhere between 0.15 and 0.20, that is greater than alpha of 0.05, we fail to reject our null hypothesis. We do not have enough evidence to conclude that the mean dissolved oxygen level is less than 5 milligrams per liter. All right, one more example, finding a test statistic. So here's what we're looking at, a sample size, let's see, so 3.17. But since we're looking at not equal to, we're looking for both of these areas, which means we're going to find this one and multiply it by 2. So degrees of freedom is going to be 28. So we're going to look at the row of 28. Okay. And we're going to find the test statistic that is between, or where 3.17 is between which two test statistics. 3.17 is going to be between these two test statistics, which we look up. So that means our p-value is going to be between 0.001 and 0.0025. So 0.001 and 0.0025. However, since that's just representing one of these areas, we have to multiply these by 2 to get our p-value, 0.002 and 0.005. So our p-value is somewhere between these two numbers.